what I want to do is kind of go through a couple more examples so you can sort of see these examples worked out. You sort of have some demonstrations that you can use to follow off on. So what I want to do now is an example of what's called a right-tailed test. So I'm going to go ahead and clear the screen here. Now, if you go back to the slide that we had a moment before for the last example, what we saw was that we shaded the critical region, or the region that would have been surprising to us if we found a result there, was to the left. Now we're going to do an example where it actually goes in the other direction, where we're going to see that what surprises us would be in the quote unquote the right tail of the distribution. Okay, so here's the scenario that we have this time. Example 1b. Okay. For another midwife tending a different village, she too oversaw 630 births in the past 10 years. Again, how convenient. She claims she could increase the likelihood of twins being born. If 11 births were multiple births, what can you conclude and why? All right, so let's actually walk through this one. So, and we'll go through actually go through the 7 steps. So step 1 is to state the claim. I'm not sure why that's coming up so very small. So the claim is that the midwife can increase the multiple births. Okay, so increase means greater than, and of course, in this case, we would compare it to the general population. So we would now want to state our 2 hypotheses. So our first hypothesis would be, putting this as the alternative, we're saying K, the number of births, would be greater than 1/90 times 630, which again we know to be 7. So if this then becomes the alternative hypothesis, the null hypothesis would be the exact opposite of this. So the exact opposite is that K would be less than or equal to 7. All right, so we have step 1 is to state the claim. Step 2 is to convert the information into hypotheses. Ideally, numerical hypotheses where the null hypothesis contains the condition of equality. I can't stress that enough, because remember, that's part of what we can do is we can disprove things in empirical science, and what we can disprove is an equality statement. So that's why the null hypothesis has to have that condition of equality, i.e. K equals 7, or K is less than or equal to 7. All right, step 2 is to state our significance level, i.e. state the rules of the game. In this case, alpha equals 0.05. Okay, now, do I need to use 0.05? No, I actually don't. I could really pick any value I want. I could pick 0.02, I could pick 0.01. And now from here, what we want to do then is sort of sketch a version of what this would look like. Well, let me see if I can do it on this screen again. This may not come out the best, so bear with me here. So what I'm going to do is I'm going to try to draw a sketch of the bell curve. All right, that's not too bad. It's going to, no, that's what it thinks I meant to draw. Okay. And we know that the center of this would be at, so the center of this would be here at, I actually do want that to be a line. So this is at K equals 7. Okay, so K equals 7. Okay. Now, what would be the surprising region here? Well, if k is 7 or less, then I wouldn't be surprised if I found values down here, but I would be surprised to find values up here. So I would be surprised if I found values in this region up here, or going this way. Okay, so this is what I would consider the surprising region. So this is the critical region. So I values up and above. Okay. So now, again, I know my test statistic in this example. The test statistic in this example was k equals 11. That's how many births there were. So that's the test statistic. So what I need to do now is convert this. So the question is, how likely, so I want to know what is the probability of seeing that or something larger. So the p-value really will be, so my p-value is the probability of k greater than or equal to 11. Okay, so this is the p-value that I'm trying to calculate now. All right, so I'm going to use a little bit of the arithmetic of probabilities here. I know that this should be 1 minus the probability that k is less than 11. Now, why am I doing this? Well, because I don't have a greater than or equal to function in Excel, but I have a less than or equal to function. Now, remember, k is a whole number. So if k is strictly less than 11, then that's really the same thing as saying that 1 minus p of k less than or equal to 10. And that is a number that I can punch into Excel. Okay, so using all the information we have so far, punching this all into Excel would be equals 1 minus binom dist. I put in the value 10, 630, 1 over 90, and I would say true. I'll walk through each of these and I'll kind of highlight the colors here for each of these to sort of draw them back to what we were just talking about. So again, the value 10, where did 10 come from? Well, 10 was really from our, so 10 here, this value 10, let me try that again. So this value here of 10 is actually k, which is 11, but it's actually k minus 1 in this context. Okay, so this is k minus 1 because I want to find the probability of k greater than or equal to 11, so I want everything that's not 11 and above, which means I want 10 and below. Now, the values here, so these values here, try it again. These values here these values came from my hypothesis. Now again, I was hypothesizing k is less than or equal to 7, but I'm also hypothesizing information about the distribution, which is that the proportion is 1 over 90 and the sample size was 130. Now, why is it true? Well, again, the true part was because it's always, so the true part is always because it's the sample that we're observing or something more extreme. This is that or the more extreme part. Now, if I punch this into my calculator, what I'm going to get, or if I punch this into Excel, the value we're going to get is 9.7%. So, sorry, let me just go back. Step 1 is state the claim. 2 is state the hypotheses. 3 is state the rules, the significance level. 3 is to draw, 4 is to draw the graph with the critical region. 5 is to state your test statistic and p-value. And now this p-value is, comes out to be, so the p-value is 9.7%. And 9.7% is greater than, so this value is greater than alpha, which is 0.05. So in this case, it actually doesn't matter if I'd actually picked an even larger value, a smaller value like 0.02 or something like that. So the implication then, so this implies this is not an unusual observation. This is not an unusual observation. Thus, we fail to reject the null hypothesis. Okay, so that's step 6. What are we going to do with the null? Are we going to reject it or fail to reject it? P is greater than alpha, so this is not unusual. It didn't fall in the critical region. The critical region are the values that would have surprised us. This isn't there, so it doesn't surprise us. So at this point, we have no reason to think the value's actually wrong. So we finally, so wrapping this all up, we state our conclusion. So if I go back to the flow chart, did the original claim contain the condition of equality? It did not. Did I reject the null? I did not. I failed to reject. So I want to state my conclusion as there is not sufficient evidence to support the claim that, so I'll just borrow that language exactly as it's there. There is not sufficient sample evidence to support the claim that the midwife can increase multiple births. Now, did she have larger than the population average? Yes. But is there enough evidence to claim that that's something that would happen on a regular enough basis, or that's something that she has control over? Probably not. Yeah, oh yeah, so our claim was that the midwife can increase. So that means that the K was greater than 7. So that's where it's not equal. And that's a good thing because if this is not, if this doesn't have the equality condition, then our straw man, i.e. the null hypothesis, will. So if I can disprove this, then this is true. Does that help?
Okay, so if the alternative hypothesis was like K is greater than or equal to 7, then would it have the condition of equality?
Yes. So if we were saying that the midwife can cause at least 7 births. Now, the question would be why we want to make a claim that has that additional level of specificity if it's not necessary. But yes, that is possible. That is possible.
Okay, that makes sense. Thank you.
Now, what I'm going to do is I'm going to tweak this just a little bit to show you. So what I'm going to do is now I'm going to kind of show you what happens when we take it to the extreme. Let's say for a second, so previously we looked at this with K equals 11. Let's say she was really good. Let's say she had K equals 25. Right, so let's say out of the 630 births, she had the probability of, she actually ended up with 25 births. Now again, so just to emphasize what we're doing here is, so I'm sort of giving a new scenario here where we're looking at a completely different, we're kind of looking at a completely different problem here. Okay, so we're kind of looking at a different situation here. So let's pretend for a second that it had been 25, not 11. All right, well, kind of, I'll walk us through that logic again of the p-value for this. So the p-value would then be, try to stick with the same color scheme here. So what the probability of 25 or more under this scenario, which would be 1 minus the probability of K less than 25, that's using the rule of complements. K has to be a whole number, so it's 1 minus the probability that K is less or equal to 24. That's what we can put into Excel. So I'm just going to borrow what's up here. So the only thing that would change up here is this 10 would now be a 24. All right, so let's go ahead and copy this. So the 10 here becomes a 24. And this value turns out to be, if we punch this into Excel, 8.3e minus 8, which again, if we were converting this to notation, this would be 0.000000083, or said another way, this is about 1 in 12 million. Okay. So this is the p-value if she had had 25 births. Well, what would we do in this case? Would we reject or fail to reject the null? Is this unusual? If the null hypothesis is true, then yes, this is definitely unusual. So this suggests that we would actually reject the null. So there are times when it gets a lot more extreme, in which the situation where we end up saying, yes, we definitely would be rejecting the null, becomes a lot more obvious. Okay. Now, the examples that we just went through here are what we call one-tailed tests. So technically, the first example we did was an example of a left-tailed test. The second example, this one we just did, is an example of a right-tailed test. So let's do an example of one where we actually have a two-tailed test. So let's do a two-tailed test, and let's do it in the context of, let's do a slightly different context. We'll move away from the population proportions for a second. Okay, so what we have here is an example using correlations. So you believe SES and the number of extracurricular activities are correlated. In particular, you believe they are negatively correlated, but you're wishing to show first that there is indeed a non-zero correlation. So the researcher thinks there's a negative correlation, but we want to first just say, hey, there's some correlation, okay? So you obtain data on 15 students. What correlation is needed to prove there is a correlation at an alpha equals 0.02 significance level? And then we would explain what we would conclude with a finding of R equals negative 0.615. Okay. Now, in this case, the negative correlation, so SES in this case is coded as, it's actually kind of coded in reverse, i.e., the higher your SES score means the more socioeconomic distress you are in, as opposed to having more wealth. So as SES difficulty goes up, the expectation is you'd be able to attend and participate in fewer extracurricular activities. Explained. That's why the correlation here is negative. All right. So our claim, or at least the claim of the researchers, the claim is that these are indeed correlated. I think I was using orange for the claim. Okay. So if we're converting these to, so what I'm saying here is that what I would first just write out what I think this means. That means there's some value rho, which the rho is some number, but most importantly, it's not zero. So this is not a condition of equality. So this would be my null hypothesis. That's sort of the logic that we'd want to use for this. Right, so that's my alternative hypothesis. So that becomes the alternative hypothesis, which means the null hypothesis is the exact opposite of this. What is the exact opposite of not equal? Well, it would be equal. So step one, state the claim in plain English. Step two, convert them to hypothesis statements. Now, step three has already been given to us. We don't actually have a choice for this one. So if I'm actually looking at this up here, I've already been given the significance level. So I've already been given the significance level. Alpha equals 0.02. So sometimes it's given to you, sometimes you actually get to pick it. All right, now the question then is, well, how do we proceed with this? So let me go ahead and save this. I think I need to bring up the next picture. Yeah, I need to bring up the next one. Part 2. All right, so what we want to do is we want to shade the critical region. Well, I'm actually, so with a two-tailed, so there's the, I can actually get the critical values directly. So let me pull the critical values from here. So the critical value that I want would be this one here. Why is that the one I want? Well, I had 15 participants, and this is the value that, this is the critical value beyond which, so this at a 0.02 significance, this is what I would expect by random chance to happen if there was no correlation. So in other words, if I kind of come up here and I draw a plot of this, so here we have the critical values. So we'd have a value at, this value would be at negative 0.5. I'll go ahead and type this in, make my life easier. So this value would be at 0.592. This value would be at plus 0.592. Again, that's how we interpret these values, which means from the standpoint of the critical region, I would be surprised if I found values down here, or I found values up here. So this is the critical region. These are the critical regions. Okay. So again, if the null hypothesis is true, remember the null is that there is no correlation. The null is that there is no correlation. If that's true, then the usual range of values would fall in here, which means the unusual values would fall out here. So I believe our value was here at negative, so that would be purple. So our value is here at negative 0.615. Okay. So we still followed all the same steps. We stated our claim. Step 2 is we wrote our hypotheses. Step 3 was we set the rules. We stated our significance level. We drew a picture. Now I had to get my critical region from my critical value from a table. And if I had had a different alpha level, I would have had to reference a different table. So in this case, it would have been a higher value, 0.641, which would have been just beyond, and I would have failed to reject there. But in this case, we have our critical region, we have our test statistic. I'm not going to calculate a p-value here, but I am going to note that in this context here, p is less than alpha. So here, p is less than alpha, which means we reject the null. Okay, because the test statistic is in the critical region, i.e. the correlation. Okay. So because of that, we reject the null. So p less than alpha or the test statistic in the critical region both lead to the same conclusion. Now, if on the other hand, we had used a different alpha level, if we had used the alpha level of 0.641, if I had used this, if we had used this value instead, then our R critical value would be Pete's sake, I hate writing on these things. Plus or minus 0. I gotta type this. I give up. Plus or minus 0.641, in which case, if I come back up to my picture, my critical region would have moved out further to the left and to the right, and then my negative 6.15 would have fallen inside the range of usual values, and I would have failed to reject the null in this case. So the moral of the story is that arbitrary choice that you pick for your cutoff values, it is just that. It is arbitrary. And depending on where you put it, depending on where you set it, you end up with the possibility of ending up with two different conclusions. So if I use a significance level of 0.02, this is a significant correlation. But if I use a significance level of 0.01, this is not a significant correlation.